A tire manufacturer is considering a proposal to advertise the average durability of the company's tires. Records kept on a sample of 100 tires yield a mean of 50,000 kilometers with a standard deviation of 5,000 kilometers. Using the 95% confidence level advised the manufacturer as to the limits of the average life of all tires. Similar, we use a 5-step model to identify the confidence interval for the average life of all tires. First step is to describe the population parameter of concern. We need to identify the 95% confidence level for the limits of the average life of all tires. So the mean life of all tires, it's the parameter of interest in our question. Step 2 is to specify the confidence interval criteria. First of all, we have to check the assumptions. We can consider the average life normally distributed because we have a very large sample. We have a sample of 100 tires. We need to identify the probability distribution and formula to be used. We can use the standard normal variable z with a standard deviation for the sample of 5,000 kilometers because we have a large sample with n larger than 30. So we can use the standard deviation of our sample when we calculate the error. Once more, we can do this one because we have a large sample where n is larger than 30. We have to determine the level of confidence. The question asks for a 95% confidence. Step 3 is to collect and present information. The sample information is given in the statement of our problem. We have a sample of 100 tires with an average life of 50,000 kilometers. Also, we know for the sample that the standard deviation for these 100 tires is 5,000 kilometers. Step 4 is to determine the confidence interval. In order to calculate the confidence coefficient, we use the normal table and the normal curve. We are looking to build a 95% confidence level. So our error is 5%. Due to the perfect symmetry, we have 2% more than the upper limit of our interval and 2.5 less than the lower limit of our interval. We need to identify this coefficient, the cutoff point that will separate the 2.5 error. So, in order to read this z value, we use the normal table, and the area that we can read from the table is the area between z equal to 0 to this cutoff point. Due to the perfect symmetry, taking in account that the area below the entire normal curve is 1, and we have half of the area decimal 5, if we subtract 2.5, the area of interest will be 47.5%. So we are looking to calculate z corresponding to an area of decimal 4750. Let's check the normal table. So we are looking inside of the table and we try to identify an area of decimal 4750. So we can see this area here. Z corresponding to this area is 1.9, second decimal is 6. So if we return to our previous slide, we have Z 1 decimal 96. And now we can calculate the error. So this will be this Z value that we just read from our table times the standard deviation of our sample divided by square root n. So will be 196 times 5000 divided by square root 100. So this will give us an error of 980. So to calculate the lower confidence limit, we subtract this error from the mean life of our sample. So it will be 50,000 minus 980. So this will give us 49,020 kilometers. So this will be the lower limit. The upper limit will be 50,000 plus 980. So this will be 50,980 kilometers. So this will be the upper limit. Step 5 of our model is to state the confidence interval. So 49,020 kilometers to 50,900 kilometers, it's a 95% confidence interval for the true average life of all tires.